It's recording. First things first, like we were talking about, no class on Friday, right, for Good Friday, and also no classes on Monday. If you have Monday classes, we don't, but if you do. So no class. Oh, I was writing in black, and I know it seems really weird, but I don't like the look of the black pen on here. But anyways, so I go for blue. No class on Friday. Also no classes on Monday, but we don't, that doesn't really apply to us. Yeah, just to mix up the end of the term, right? When all the important stuff, it's like, okay, we've built up to this, now take a break. That's okay. All right, so what we're gonna do today is we're gonna finish chapter 3 and then move into chapter 4. So there are like two distinct concepts. There's still applications, so of derivatives. Remember we did related rates last day, right? So just for some quick review, right, we did, and I don't actually think we'll have time to do a review, but I posted lots of extra examples and even a video of the related rates. So make sure that the related rates are good. And then today we're going to do 3.10. So related rates was 3.9. I know the section numbers only really matter to me, but that's how I keep them straight. So 3.9 is related rates, and then 310 is linear approximations. And I don't know, we'll talk more about it when we start, but I don't really get the point of them. I know that they were important at one point when we didn't really have calculators, but I don't know. We're just going to do them. We have to do them. So we're doing it. Something that I do understand the point of is 4.1, which is on maximum and minimum values. Maximum and minimum values. Okay. And so initially I didn't have 4.1 on the quiz, but then I remembered we don't have class on Friday. So I am gonna kind of readjust the quiz and include 4.1. So quiz number 7, I think it's number 7. Quiz number 7 is gonna be on 3.9, 310, and 4.1. And how I'm doing these later quizzes is I'm looking at the final exam and I'm making sure that you'll be able to do those. So it's basically final exam prep, right? And so because we're getting so close to the end, right, I really want to set you guys up for a beautiful final exam. So I do need to make that adjustment. So the quiz will be available later this afternoon. Hopefully no one was gonna jump in and do some related rates right after class, hopefully. Okay, so let's see here. All right, anything else that I wanted to talk about? I don't think so. We do have a test 3, but test 3 isn't until the 14th. Yeah, so we'll do, so quiz 7 is going to be this week. Mostly because, and I can, like I said, I can extend it because we don't have class on Friday. right? I can extend it, just let me know, but I'll make it due for Friday, just like normal, and then it'll be out of the way, and yeah, it's just kind of nice to get it out of the way. It's annoying, but nice. And mostly just to kind of stay on top of things for the last 2 weeks of classes here. So we do have test 3, but like I said, these quizzes should be doing a pretty good job of setting you up for success. All right, so I cannot think of anything else that I wanted to say here. So 3.10 is the last section that we're doing in chapter 3. And it is on linear approximation, and differentials, which we're not really going to talk about. I'm just going to show you what you do for the assignment questions. So we know, right, that the tangent, so we've talked about the tangent line, we talk about the tangent line, I want to say every day, right? And so we know that the tangent line close to a point, right? And so we know the tangent line at x equals a, let's say, right, is approximately the same, right? And so here we get to this linear approximation, is approximately the same as the actual function at a, okay? Is approximately the same as the actual function at a. At x equals a. Okay. So what I want to do is, well, I'm going to try to do a graph. So let's say I've got this function here, and I want to look at some x equals a. If I draw my tangent line here, right, then I know that around a, right, so some interval around a, very close to a, then if I kind of zoom in, and this is where my art skills are gonna probably fail me, but if I zoom in here, whee, what we would be looking at might look something like this, right? So it's basically the same for some stretch of time, right? So let's see here. What we can do is, if this function, so this blue function, is difficult to evaluate, what we can do instead is we can say, okay, well, how about I can just make a series of tangent lines and do approximations of the function, right? So in theory, you could do little tangent lines all the way along and approximate the function. Okay. So here, given a function y equals f of x, we can approximate the function. We can approximate the function by the tangent line over small intervals. Okay, so what I'll kind of follow it up with is, imagine that the function is really difficult to evaluate. Now, with our computing power that we have, even a basic calculator is able to do these calculations. So you do have to kind of step back and think before calculators how powerful that would be. But like I said, I Googled it, I tried to figure out, you know, why is this so important? And I know calculators are using approximations. They're not necessarily using linear approximations all the time, but linear approximations are obviously the easiest ones to deal with. Besides kind of simplifying calculations, I couldn't really find an answer, but it's something that we have to learn and something we have to do. So we're doing it. And the idea is that evaluating a straight line is going to be easier than evaluating some difficult function. And so if f of x is difficult to evaluate, it will be easier to evaluate a linear function, right? A linear function, y equals mx plus b, that's easy to evaluate. So it'll be easier to evaluate a linear function and use it as an approximation. That's kind of the best I could come up with. So there's probably better explanations. I couldn't find any. So, all right. So the whole idea is we're going to use the equation of the tangent line to evaluate a function or approximate a function at values close to some point A. Now, let's just review, because we know how to find the equation of the tangent line. We know how to find, it's like, I feel like it's all I'm getting you guys to do. Find the equation of the tangent line. Find the equation of the tangent line. So we know how to find the equation of the tangent line. The equation of a tangent line in general. First, what do? We have to find the slope, right? At some point A. And maybe I'll follow it up with of a tangent line at x equals A. Okay. So what do we have to do? Well, we have to find the slope. So first step, find the slope at x equals A. Well, the slope is the derivative evaluated at A. We know that. We've used that a bunch. Right? So of course it's going to involve finding the derivative. Everything that we do from here on out is going to involve finding the derivative. So we spent a lot of time developing in chapter 3, developing the tools to be able to do these derivatives. And now we're just kind of testing those tools. I know implicitly is a trigger word now from implicit differentiation. But we're kind of testing those tools implicitly by making you do these derivatives kind of in an applied setting now. So related rates was kind of the first time that we did that. And then now from here on out, we're just going to use these differentiation rules to find the derivatives.
So what you're saying is we're done and building the tools to build the tools now that we actually get to use the tools.
Exactly. Well said. Yeah, you got to build the tools to build the tools to build the thing. Yeah. Perfect. Yes. Okay, so then if we're interested at x equals A, then of course there is some output value f of A. And so use the point, right? Because if we're using the point slope form of a line, blah, 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 we need a point, we have the slope. So we're going to use the point A, f of A. Notice that here, this is my x, and then the output is just, I'm just going to use f of A as the output. That's fine. In the point slope form of a line, which we have been using a lot as well, and if you don't have it kind of highlighted on some sort of kind of formula sheet style thing, then of course you will want to add it. Y minus y naught is m times x minus x naught. Or potentially at this point, you've just got it memorized. So the point that you know is x naught, y naught. So you can fill those in, but then we also have the slope. So here, this becomes y minus f of A is the slope, which is actually the derivative at A, times x minus A. If we rearrange this, it becomes y equals f prime of A times x minus A. I'm not going to expand that out because usually it's just easier if I don't. And then plus f of A. What we just developed is the linear approximation at x equals A. Okay. So this is the linear approximation at x equals A. Okay. And maybe I should put it here. How we're going to denote this is we call this capital L of x for linearization. Or linear approximation, it doesn't matter. This is the exact same as the equation of the tangent line, right? So what we're doing is not new. It's just that instead of calling it the equation of the tangent line, we're calling it the linear approximation at x equals A, which kind of thinking about what those graphs look like, if you zoom in on them, it kind of makes sense. Or it really makes sense, rather. Okay, I wanted to grab, where is it here? This one. So, oops. What we have, right, we've established that, and this is what we just developed, right? So here we're just summarizing what we just said. We're writing it as f of A plus f prime of A times x minus A, just reversing the order of addition. It doesn't change anything. So this is the linear approximation at A. So what we're going to be using or leveraging is that f of x is roughly equal to L of x for values of x close to x equals A. And that's going to be really important. The values that we're talking about, the x values that we're talking about, have to be close to that value of A, because as we saw when we did like a fake zoom in of, bless you, David. When we did like a fake zoom in, is that line is only a good approximation for a short amount of time, right? For a short interval. And so so we need to keep that in mind. So we have to have values of x that are close to A. All right, I want to do an example. Let's do example 1. Maybe I'll put it on a fresh page here. We're asked to find the linearization of the function f of x is the root of x plus 3 at a equals 1. And then we're going to use it to approximate the numbers the root of 3.98 and the root of 4.05. And here's where my kind of hang up. We could just calculate these on our calculator, right? But we are going to use the linearization to do it. Okay. And then we're going to talk about, so then we do the calculation on our calculator, and we're going to be able to determine if we have over or under estimates. And just visually, an overestimate is when the line is kind of on top of the curve, and an underestimate is when the line is below the curve. So maybe I should put, I've got a little bit of room here up above. So maybe I'll make a little note here. Note, the linearization will either be an over or underestimate. And graphically what that looks like is like this. So let's say I've got kind of this curve behavior. All right, let's talk about some 2 points here. This would be an overestimate, and this would be an underestimate. Should probably write the whole word. We are just going to determine if we have over or underestimates using our calculator. So you don't have to do it graphically, but I just want you to see what it looks like graphically, right? And so if you've got this kind of, I'm really bad at convex, concave. I feel like this is concave. Anyways, we'll get there. Then of course the tangent line is going to be kind of pushed below the curve versus here the tangent line would have to be on top. So it depends on the curve. But we're just going to use our calculator. So now find the linearization of the function. So basically what we're going to do is we're going to find the equation of the tangent line at a equals 1. So I'll break this into steps, but I'm really good at forgetting to name the steps. I'll do step 1 and then I never mention another step again. So, and now that I mention it, I have done that in my notes. Just have step 1, no more steps. Still true, but not very helpful.
Step 1, draw a circle.
I'll try
Step 2, draw the rest of the owl.
Yeah. Yeah, so anyways, I'll try to figure out the steps here. Anyways, first we're going to find the equation of the tangent line at x equals 1. So find the equation of the tangent line. I feel like that can be broken up into multiple steps, right? Find the derivative, that's the slope, and then generate the line, but here we go. So find the equation of the tangent line at x equals 1. So far so good, right? We know how to find the equation of a tangent line, so we have f of x is the root of x plus 3. We know how to find the derivative of that, right? The derivative of f of x is 1/2 times x plus 3 to the negative 1/2. Technically times 1, right? The derivative of the inside is just the derivative of x plus 3, which is just 1. So can tack that on there. So then we get 1 over 2 root x plus 3 is my derivative. So now at x equals 1, f prime at 1 the derivative is 1 over 2 times the root of 1 plus 3. The root of 1 plus 3 is 2, right? Because 1 plus 3 is 4, square root of 4 is 2, so pretty nice and easy stuff so far. So I get a slope of 1/4 or 1 over 4, which is m at x equals 1. Here's my hang up. Why am I going to use the root of 1 plus 3 to figure out approximately what the root of 1 plus 3 is? That to me, I don't know why I can't get on board. It's just, I don't like it. So if you're feeling that way, then that's okay. It's just like a weird thing that we do. Okay. I'm sure there's a really good reason why we do it, but I don't know it. So now we know the point. The point 1, f of 1 is 2, is 1, 2.
Is this step 2?
Pardon?
Is this step 2?
No, because I named the first step was this all-encompassing find the equation of the tangent line. Okay. I should have broken that up into little sub-steps. But it's like, here, do this big load of work. Step 1. Step 2, use the tangent line, which is what it will be. Okay, so let's see here. So we know the point 1, 2. So now we can construct the tangent line. And you know what? We can just, I default to just using the point slope form of the line, or if you prefer, you can actually just go and plug it straight into, straight into L of x. That's fine. In fact, maybe that's what I should do. Just to show why we would need that. But you can just get there from the point slope form of a line too. Right. So L of x is f of a, which is 2, plus 1 over 4 times x minus 1. So the linearization is 2 plus 1 over 4x minus 1 over 4. Now I want to collect this 2 and 1 over 4, which means I need to rewrite 2 as something over 4, which is fine, right? 8 over 4. 8 minus 1 is 7. So I get 1 over 4x plus 7 over 4 after I find the common denominator and subtract. Okay. This is only true when x is near 1, right? Because that's what we've been hinging all this on. So when x is near 1, Okay.
So you're saying it's like the limit as x approaches 1?
Say that again.
So you're saying it's like the limit as x approaches 1?
Pretty much. Yes. Pretty much. So kind of want, but what we were trying to do, now I'm ready for my step 2. Step 2, because what we were, so this is the linearization close to x equals 1, but what we actually wanted to find was we wanted to approximate the numbers of the root of 3.98, which is 3 plus 0.98. 0.98 is close to 1, right? And the root of 4.05, well, 4.05 is 3 plus 1.05 again. 1.05 is close to 1, right? So now we're going to approximate these numbers using the linearization. So step 2, approximate the values using L of x. So if we want to approximate the root of 3.98, that's the same as the root of 0.98 plus 3, which tells me that x is 0.98, which is close to 1. So now just remember that x is 0.98. So when you do your linearization, right, L of x, remember, is 1 over 4x plus 7 over 4. What you want to do is L of 0.98. Right, because x is 0.98. So you don't want to do 3.98, just 0.98, which is going to be 1 over 4 times 0.98 plus 7 over 4. And here, I guess maybe, so I'm talking myself into it, right? If you imagine you don't have a calculator and you don't know how to take the square root of 3.98, but you do know how to take the square root of 4, right? Like I was kind of mocking earlier, then maybe this is a good way, right? Maybe I'd rather be dividing 0.98 by 4 instead of taking the square root of 3.98. So anyways, there, I talked myself into it. Great. 1 over, so 0.98 divided by 4, I get is going to be equal to 1.75 plus no, I did them in the different order. 0.245 plus 1.75. 7 over 4 is 1.75. So then I get 1.995. And then what we said was f of 3.98 f of 0.98 is roughly equal to L of 0.98, right? So it's roughly equal to 1.995. using a calculator, and maybe I'll call this kind of step 3, but we're going to do it for 4.05 as well. So kind of breaking it up into a tree. Step 3, over or underestimate. Using a calculator, we find that the root of 3.98, again, and of course it's just an approximation because we can't see all the decimal places, but it brings us to 0.9949937334, which is slightly less than the approximation that we found, right, of 1.995. So our approximation is an overestimate, right, because it's slightly over this actual value. So therefore, our linearization is an overestimate and maybe I'll just leave it there. Back to kind of step 2 for the other approximation. What did I say at the now I'm going to approximate the root of 4.05. So again, I need to break this thing up, right? The root of 4.05 is the same as the root of 1.05 plus 3. So then, oops, x must be 1.05. So L of x is going to be 1 over 4 times 1.05 plus 7 over 4. So L of x is 1.05 divided by 4 is 0.2625 plus 1.75, putting me at 2.0125. And then following the same layout, right? So then f of, you know what, I should do L of 1.05 in here. F of 1.05 is roughly equal to L of 1.05. So it's approximated at 2.0125. Step 3 then, again, is to determine if we have an over or an underestimate. Step 3, over or under. Well, from a calculator, or using a calculator, we find that the root of 4.05 is roughly 2.012461118. Therefore, we have an overestimate again. Constantly having an overestimate kind of depends on the function, right? But if we think about what the root of x plus 3 looks like, right? y equals the root of x plus 3. And here I am at -3. It makes sense that this tangent line would always just be on top, right? There's no point that it would ever be kind of underneath. No, even because it's going to slightly increase and kind of bow out like this, right? So if we know what the graph is going to look like, then we can kind of convince ourselves that, okay, an overestimate, it makes sense. Okay. Let's do another example. This one I added in. As you can tell. Okay. So now we're going to find the linearization of this thing, 4 times the root of x squared minus 9 at x equals 5, because ultimately what we want to do is we want to approximate f of 5.1. So we need x to be close to 5. So here we go. Where did I put those? All right. The linearization is, well, L of x is f of a plus f prime. So we have to first find the derivative. I'm tempted to not break it up into steps. Yeah. If f of x is 4 times the root of x squared minus 9, I can rewrite this, right, to make it easier to differentiate. 4 times x squared minus 9 to the power of 1/2. So then the derivative is going to be 4 times 1/2 times x squared minus 9 to the negative 1/2 times the derivative of the inside. The derivative of x squared minus 9 is 2x. Things simplify a little bit here. 2 divided by 2. So that's nice. And then I end up with 4x over the root of x squared minus 9. And then we want it at x equals 5. At x equals 5, f prime at 5 is 4 times 5 over the root of 5 squared minus 9. So 20 divided by the root of 25 minus 9. 25 minus 9 is 16. Square root of 16 is 4. So I get a nice slope of 5, positive 5. And at x equals 5, the point that we have is 5, f of 5. Well, f of 5 is 4 times the root of 5 squared minus 9, which we actually just found to be 4 times 4. So the point that we have is at 516. And all of this is just to build that linearization. So L of x is 16 plus 5 times x minus 5. Can expand this out, and I get 16 plus 5x minus 25, which is 5x minus 9. So to approximate 5.01, right, then f of 5.1, or sorry, I think I said 5.01, but it's 5.1, is roughly L of 5.1, which is going to be 5 times 5.1 minus 9. 5 times 5.1 is 25.5, and then minus 9, which is 16.5. And does it ask for... So here, it only asked us to use it to approximate f of 5.1. So we're done, but just to kind of seal the deal, right, let's figure out if this is an overestimate or an underestimate. Just do kind of a side note here, versus f of 5.1, which is actually equal to 4 times the root of 5.1 squared minus 9, which is roughly 16.4972725. So therefore, L of 5.1 is an overestimate, which makes sense again because we know the shape of a root function. And this is from a calculator, just in case didn't know where it came from. Okay. So the last part of this section is on differentials. Now, differentials, like I said, we are not really going to talk about them, but differentials, if you look at the handout, the differentials we've called dy, dx, those are differential operators. And so what we're going to do for us, the takeaway from this differential section, it gets a little bit weird, a little bit hokey, but I want you to ignore that. Don't worry about that. But there will be questions that ask, find the differential of this function. Okay. And so what you're going to do, oops. Is use this, oops. So here, this is the differential. Notice that all that's happened is we've taken dy dx and then we've multiplied the dx over, which feels weird, but you know how to find the derivative of some function, and that is dy dx. And then the differential is just multiplying this dx over. So the question will ask, find the differential of f of x. Okay. So what you're going to do is say dy dx is f prime of x, but really just the only change is that you're going to multiply that dx over. Okay. So you're just going to find the derivative and then tack on a dx, shifting that dx over from the left-hand side to the right-hand side. Right. So find the derivative then tack on dx at the end. I'm trying to keep it on the same page here. Okay. That's all you're doing. And when I say tack on the dx, you don't do anything. So if you want to find the differential of, let's say, I don't know, x squared, right? The derivative of x squared is 2x, and then the differential is 2x dx. Okay. So here, only because I'm trying to keep it all on, not flow over to the next page here. Of f of x, let's say f of x is x squared, just to keep it nice and simple. Then the answer is 2x dx. And technically it's dy. Yeah. So you just tack on that dx, or I saw some of the questions have like d theta, dt, depending on what you're differentiating with respect to. You just kind of float that over to the other side. Okay. Any questions before we start chapter 4? And we're only doing a handful of sections in chapter 4, but they're kind of the most fun sections, so that's why I'm hurrying to get there. Let me know if you want to break or if you want to just end early. I'll start chapter 4 and let me know what you want. I'm good either way.
I'm good to be continuing.
Sorry, say that again.
I'm good to be continuing.
Awesome. Cool. Let's see what Carly says. Maximum and, yeah, I'll just end early. How about that? Maximum and minimum values. So derivatives, right? So this course is on derivatives, so differential calculus, and then Calc 2 is going to be on integrals, which is finding the area under the curve, or then moving to 3D objects, kind of finding volume and that kind of fun stuff. And they're related, don't worry. So there's kind of two different types of calculus that we can do. So we're doing differential calculus, and because we're finding derivatives, and where we use it the most is in optimization. Now, optimization is this huge field. You know, you want to optimize runtime, or you want to optimize efficiency or cost, or optimizing can mean minimize or maximize, right? So we understand optimize is one of those two, and it depends on what you're talking about, right? If I would say, oh, I want to minimize cost, that's an optimization. If I maximize cost to make a thing, then that's really bad, right? I want to maximize profit, right? So depending on what we're talking about, optimization can be either a maximum or a minimum. And so optimization can mean either minimize or maximize. And the math department at UBCO actually has a really good optimization kind of section. So, and it's pretty big. So, so that's pretty cool. And what they're doing is optimizing stuff. So, can you tell I wasn't part of the optimization? They optimize stuff, but I know they're really big and they publish a lot. So pretty impressive. So optimization, you're either minimizing or maximizing. Graphically, we know what that looks like, right? You're either at a peak or a valley. And I put some, I cut it short, but I put some examples here. Oops, this is the one I want. So optimization problems are things like, what's the shape of a can that minimizes manufacturing costs, right? And then what's the maximum acceleration of a space shuttle, right? So of course, these are all important things to know. Okay? And what we get is we could have a graph that looks like this, right? And so what we need to be able to do is we need to be able to differentiate, haha, pun intended, I guess, not really. We're going to have what we call absolute maximums and absolute minimums. So overall, these are the absolute maximum and minimum points. But then we're also going to have things like local minimums, right? So here, on this little interval, this is a minimum, this is a minimum, right? And this endpoint is a minimum as well, right? So we need to figure out which of these is the absolute minimum. Looks like probably this guy here, f of a, because it's just slightly below all those other minimums. But what we do is we say, well, we're going to kind of hats off. These are also minimums. They're called local minimums. Okay? So let me grab this graph here so I can just highlight what we just said. Right, so here, this is an absolute minimum, but these are also minimums, so these are local minimums. Which I guess it says in the caption, but still. Same idea, right? For the maximums graphically, we can see the maximums easily, right? We have these kind of maximum points here, right? This would be our absolute max. And these are our local max and local max. So we need tools to be able to figure out if we have an absolute maximum or a local maximum, or identify maximums and minimums in general. Now, what we're going to leverage a lot of the time is that we already know that at these peaks and valleys, we have a derivative of 0, right? So we have this kind of flat line. So we know at a peak or a valley, the derivative, right, the slope of the tangent line, so the derivative, so the slope of the tangent line is 0, right? There are a couple of situations where the derivative might not exist. So if you have a look here, we've got this kind of cusp, which we talked about. Well, the tangent line doesn't actually know where to kind of hinge on a cusp, and so we say it's not differentiable at that point. So it's still a minimum, And we're going to talk about, you know, how can we pick this up mathematically, that behavior, even though we can't differentiate at that point. So let me just bring in these definitions of absolute max and mins, but they're exactly what you kind of expect. So if C is some value in the domain, of course it has to be in the domain, then as long as f of C is the largest output available, right, then we can say that we have an absolute maximum at f of C, or at C. Same thing with the minimum. If the output at C is the smallest that it can possibly be, then of course we have a minimum. The only difference for the local max and mins is that now we're kind of zooming in to values that are close to C, right? So not overall, but just kind of on an interval. Are these values kind of the smallest they can be on an interval? Okay. Just a heads up on things that can happen, right? Because we kind of assume that you're always going to have a maximum or a minimum, but that's not always the case. Okay, so here we can look at this graph in figure 9 and we can say, okay, well here, this is my minimum, right? And so I have a minimum at f of 2, which is 0. But even though it looks like I should have a maximum value, it actually, the function doesn't exist at that point. And so it's going to get close to that point, but it's never going to be that point. And so that's why I have no maximum value, right? So sometimes we might not have a max or a min, or maybe even both, right? Here, kind of two ways that we might not have a max or a min is, okay, well, this would be our smallest value, but again, we've got that open dot, and so it doesn't actually exist at that point. It's going to get close to it, and we'll never get, you know, right next to it. We can always go a little bit closer, and so then we don't have a minimum. And then with this vertical asymptote here, again, it's going to be approaching that vertical asymptote, but it never actually gets to that vertical asymptote. And so here, there's no maximum or minimum, right? Because it doesn't exist at x equals 0. And again, it doesn't exist at the vertical asymptote. Oh, lines. Okay, so those are just some things to kind of keep in mind, right? So we might not necessarily always find a max and a min, right? So not all functions will have a max and min. So let's see here. Let's talk about the extreme value theorem. Sounds fun, right? Let's see here. Copy. The first page, we're basically just going to talk about kind of establish the theory. There's not really a lot that we're going to do. We just need to talk about all these things. But so the extreme value theorem says that if f is continuous on a closed interval, okay, so that's two things that we're going to need to check, right? The function has to be continuous and it has to be a closed interval for this theorem to work. But if both of those are satisfied, then f attains an absolute maximum value, f of c, and an absolute minimum value at some numbers c and d in this interval, right? So it assumes that it's continuous, which means it's differentiable. And as long as we're talking about some closed interval, notice here, this would be an open interval, right? Here we would have kind of an open dot here. So that's why we need closed intervals, because we need it to be evaluated at the endpoints as well. So kind of hinges on two big players, continuous, and you have to have a closed interval. So that's the extreme value theorem. And I also grabbed a graph. So all of these functions are continuous, right? And they're on a closed interval because all of these dots are they're all closed, right? So we're talking about a closed interval, and what the extreme value theorem says is that, okay, if you have a continuous closed interval function, then you will always find a max and a min. Okay? And so those maximums might be in the interval, and maybe, well, now we're talking about the minimums here, right? Maybe the minimum is at the endpoint, right? So they can happen, the max and the min will always happen, but they can happen anywhere in the interval, including at the endpoints. Okay. So, if we have a continuous function on a closed interval, we will always find a max and a min, or more than one, right? You could have more than one maximum if you reach the same output more than once, right? That's fine. We will always find a max and a min somewhere in this interval, including the endpoints, right? So it could be at the endpoints somewhere in the interval, and it could be at the endpoints. So again, lots of theorems in this section, but gotta build it up. Fermat's theorem. So Fermat actually ended up doing a lot for calculus, even though I guess he was like an amateur mathematician. He was actually a lawyer, and he just dabbled in math. And then he ended up developing all these really kind of important calculus things. So that's kind of cool. But anyways, Fermat's theorem says that if f has a local maximum or minimum at c, so at some point, so if there is a maximum or minimum, and if the derivative exists, then we can say, okay, well, then the derivative must be equal to 0. This does not work the other way around, right? It only works to say that if you have a local max or min, then, and the derivative exists, then the derivative at that point must be 0, right? And so note the derivative at c equal to 0 does not necessarily mean that you have a max or min. Often it does, right? So it's worth looking at. So note the derivative equal to 0 does not necessarily mean we have a max or min at C, right? So it only works one way, not the other way. And on the next page, I've got 2 examples where this can happen, right? Or kind of a mashup of examples, I should say. And I'm going to bring in, because it helps when you can see the graph too. Okay. Okay. So if we think about something like x to the power of 3, it's differentiable, right? It's continuous. And what we can talk about is, well, the derivative is 3x squared. So what we can say is, well, this thing is going to be 0 at x equals 0, right? If I plug in x equals 0, I get 0. So, so then if we just kind of went at it blindly, we would say, oh, x equals 0 is a minimum or a maximum. But like we said here, right, just because we found that the derivative is equal to 0 doesn't necessarily mean that we have a min or a max. Like we have here, right here, we're simply changing kind of the inflection here, and it's crossing kind of the x-axis in this case, right? So here, right, even though we found that the derivative is 0 because the slope of the tangent line would be 0, it's not actually a maximum or a minimum at this point. It's just kind of a pass-through. So that's something that we need to keep in mind. But also, the absolute value of x, remember the absolute value of x is like a V shape, and we know that we have a minimum here, right? Just because it's not differentiable at 0 doesn't mean that we don't have a minimum, right? And so here, the derivative at x equals 0 doesn't exist, right? So kind of 2 things to look out for. All right, good. I included the warning here. So those 2 examples kind of illustrate 2 different things, 2 different warnings, but we have to be careful, right? And say that, okay, well, the derivative, if I can set it equal to 0, it's not necessarily a min or a max, right? And we could have a min or a max where the derivative does not exist. So what we do is we kind of sum these things up and call them critical numbers. So a critical number, for some reason I have a hard time saying critical number. A critical number of a function f is a number c in the domain of f such that now either the derivative is equal to 0 or it doesn't exist, right? So these are 2 different ways that we can develop these critical numbers. Now these critical numbers are what we will use to kind of pull out potential minimums and maximums, right? So we use critical numbers. Which I'm going to write kind of capital C, capital N, and then S numbers. we use CN, so critical numbers, to identify potential minimums and maximums. Because these are two different types of critical numbers, right? So either the derivative is 0 or the derivative doesn't exist. Notice that we'll need the derivative either way. Sometimes we split these up into type 1 and type 2 critical numbers. If you find that that's confusing, then just ignore it, right? But you do need to check both of these types. Sometimes we might call these two different types of critical numbers. Hey, I just established the abbreviation. I should just use it. Type 1 and type 2. Right, so if the derivative at C is equal to 0, then I can call that a type 1 critical number. And if the derivative at C does not exist, I'll call that a type 2 critical number. You don't need to use that, but if you find that it's helpful, then use it, right? But as long as you remember to check both cases, it doesn't matter. Local max and min values will occur at critical numbers or at the endpoints. So local max and min values will occur at critical numbers or endpoints. So we're going to use that a little bit later, but that's where we're headed, right? So first, let's practice finding critical numbers, and then we're going to build it all up to using those critical numbers to identify max and min values. So first, we're going to practice just finding critical numbers. Find the critical numbers of this function, x to the 3 over 5 times 4 minus x. You have two ways that you can go about. So of course, the first thing you have to do is find the derivative. Notice that either case for these critical numbers, right, we have to have the derivative. And then we need to identify values of C where it's either equal to 0 or it doesn't exist. So here I go again, step 1. Let's call it step 1. Step 1, find the derivative. A couple of ways that you could do this. You could use the product rule if you want to, or I'm going to just expand this out and get kind of a weird polynomial. Either way, you're going to end up at the same result. So if you did just go ahead and use the product rule, that's fine too. F of x is x to the 3 over 5 times 4 minus x. I'll just make a note of what I just said. Could use product rule or expand for a polynomial. Depending on where your mind goes, the amount of work involved is going to be about the same, so it doesn't matter. I'm going to use the expanded version, 4x to the 3 over 5 minus x times x to the 3 over 5, x to the 1 plus 3 over 5.
8 over 5.
Yeah, 4 over 5?
8 over 5.
8 over 5. I don't know why I was, thank you. Struggle city. Good. Okay. And that's not even the derivative that I'm doing. I'm just simplifying. So now we can find the derivative. The derivative of this thing is going to be 4 times 3 over 5 times x to the 3 over 5. Instead of doing minus 1, I'm going to do minus 5 over 5 just to cut down on a step. But that is minus 1, right? Minus 8 over 5 x to the 8 over 5, and again minus 5 over 5. Okay. So I get all right. I get 4 times 3 is 12 over 5 times x to the negative 2 over 5 minus 8 over 5 x to the 8 minus 5 is 3 over 5. It's possible the product rule would have made it easier, but I don't know, I didn't try it. So now, everyone's favorite pre-calc thing, right? Factoring out a negative power. Ugh, no one likes that. But the key is you're going to rewrite this x to the negative 2 over 5. You're going to rewrite this x to the 3 over 5 as x to the negative 2 over 5 plus 5 over 5, right? And then you're able to split it up. So you get 12 over 5 x to the negative 2 over 5 minus 8 over 5 times x to the negative 2 over 5 plus 5 over 5. Right, I can kind of split that up. And now I'm able to factor out the x to the 2 over 5. But also x to the 5 over 5 just becomes x, right? So I get, here we go.
Well, how did you get the? You were just multiplying for the 8 over 5. That's just multiplying.
Oh, so now I'm rewriting x to the 3 over 5 as x to the negative 2 over 5 plus 5 over 5.
Oh, okay, I see.
Because I want to factor out this guy. And this is like, people don't like factoring out negative fractions because it is a little bit weird, but not all I'm doing, but this became this. So now I can factor out the x to the negative 2 over 5, and I can also put it over 5. They both got a factor of 1 over 5. Times 12 times 1 minus 8 times x to the 5 over 5, which is just x to the power of 1. So this becomes 12 minus 8x over 5 times x to the 2 over 5 in the denominator. Okay. That was finding the derivative, right? That's why we need to know how to find the derivatives. But now there's another step, right? Kind of application time. So step 2 is use the derivative to find the critical numbers colon again. So here, f prime at c equals 0, right? You can call this type 1 if you want to. And then on the other side of the page, I'll have type 2 if you want to, where we need to identify where the derivative does not exist. So I'm going to do these side by side just so we don't have to scroll around so much. So I have the derivative 12 minus 8x over 5x to the 2 over 5. So the only time that this whole thing will be 0 is if the numerator is 0, right? And so this is going to happen when 12 minus 8x equals 0. So now I can solve, okay, 12 equals 8x. So then when x is 12 over 8 or 3 over 2, let me just make sure. Yeah. So that's the only time that it's going to be equal to 0. So that is a potential maximum or minimum value. Now, we need to look at the other type of critical number, which is where this thing doesn't exist. Now, same way that we find the domain, right? We need to pull out values of x that make illegal math, right? So in this case, we've got division. So dividing by 0 is a no-go. So this derivative does not exist when 5 times x to the 2 over 5 equals 0. When 5x 2 over 5 equals 0. Which you can rearrange, blah, blah, blah. But you can kind of see that that's when x equals 0. So these are now potential. So these are the critical numbers, but also they're potential points where we get maximums or minimums. So x equals 3 over 2 and x equals 0 are potential max and min points. That's not what we were doing in this question. It was just asking what the critical numbers were, but that's where we're headed, right, to find those max and min values. So the critical numbers are at x equals 0 and x equals 3 over 2. Good. Because I'm running low on time, what I'll do is before I post the notes, I'll include the solutions to this guide, right? But I actually want to move on because we've seen how to find the critical numbers now. This was just more practice at doing that with the quotient rule, right? But what I want to talk about is the closed interval method. So I will do this. I will bring this in. And I'll fill this in. So I will fill that in. So maybe try that one on your own and then go back and see. but we're going to practice finding the critical numbers using the closed interval method. Fresh page here. Okay. So the closed interval method, remember we've talked about closed intervals earlier. So, okay, now we're just coming back to that. So to find the absolute maximum and minimum values of a continuous function, so again, we have to have a continuous function on a closed interval, a to b. What we're going to do is we're going to find the values of f at the critical numbers. So step one, find those critical numbers and then evaluate the function at those critical numbers. Then you're going to evaluate the function at the endpoints, because what we said was the max and mins are going to happen either at the endpoints or somewhere in between, right? And then what you do is you just pick the largest and the smallest values of both of those, right? Either at a critical number or at an endpoint, and then you have your absolute max and mins. So let's do example. Oops. Find the maximum or the absolute max and min values of this function and on the interval -1/2 to 4. So first thing we're going to check is a polynomial is one of those functions that's always continuous. So because the domain is the set of real numbers, right, continuity has to do with the domain, right? So if the domain is a set of real numbers, then it's continuous on the set of real numbers. So here, this is continuous because it's a polynomial. And we're including these endpoints, so we have a closed interval. Which means we can use the closed interval method to find maximums and minimums. And that's always going to be the case for us, right? Not in life, but for us. Okay. First thing we're going to do is we have to find the critical numbers of this thing. So here, step one. Find the critical numbers. So f prime of x is 3x squared minus 6x, and that's it. You can use the quadratic formula if you want, or I'm going to factor this thing and get 3x times x minus 2. Just makes it easier, I think. So now the critical numbers, I have either f prime of x can be equal to 0 or f prime of x does not exist. Either one of those is a critical number. So now we can find where this thing equals 0. There's no division, there's no roots, so this is when 3x times x minus 2 equals 0, which now that I've factored it, I can see, and you could have used the quadratic formula as well, right? X equals 0 is going to give me 0, and x equals 2 is going to give me 0. So these are both critical numbers. What you want to check is we're only interested in this interval, right? So in the next example, if I have time, there's going to be critical numbers that are not in the interval. So then you ditch those because we're only interested in that interval. But from -1/2 to 4, both of these, both are in the closed interval. So that's good. So we're going to consider both of those. There is no value of x that I could plug in here to give illegal math, right? And so there are no type 2, and that's when it's easier to call them type 2. There are no values of x that make this derivative not exist, right? And so here we'll say f prime of x exists for all values of x. Therefore, no type 2 critical numbers. And that's fine, right? That can happen. So, step 2. Step 2, evaluate the function at the critical numbers. Evaluate the function at the critical numbers. So we want to look at f of 0. F of 0 is, and I'm not going to scroll around here, 0 to the 3 minus 3 times 0 squared plus 1, which is 1. And f of 2 is 2 to the 3 minus 3 times 2 squared plus 1, which is, I had it here, -3. These are potential maximums and minimums, right, at an output of 1 and -3. But we also need to evaluate the endpoints. So step 3, evaluate the function at the endpoints. So we need to find f of -1/2, which in the interest of time, I'm just going to tell you is 1/8. And then f of 4 is 17. And then step 4, of those, all those outputs, select the maximum and the minimum, and those would be your absolute max and mins. So of the output above, select the maximum and the minimum value. Oops. So looking at these outputs, 17 is definitely my maximum. And -3 seems to be my minimum. So therefore we have an absolute max at f of 4 equals 17 and min at, and I mean absolute min, at f of 2 equals -3. And I also included the graph of this function just to show that it all kind of makes sense. So here, right, we identified these points, right, at x equals 0, x equals 2, x equals 4, and also we evaluated at -1/2, I think it was. Yeah. And it's just over the x-axis, right? And so we know all those points, but there can only be one absolute max and one absolute min. Right? So I promised to let you go early, but I also want to do the last example. How about I'll work on it for 5 minutes and then I'll finish it up in the notes if we don't get through it. But I do want to show you what can happen because we might find critical numbers that are not in the interval and then you just toss them and then you just keep going like we did. Oops. Copy. Oops, paste image. That's what I want. So we want to find the absolute max and min of this function. And so it's on page. So we have f of x is x times the root of 4 minus x squared. So first thing I need to do is I need to find the derivative of this thing, which is going to require the product rule and the chain rule, right? And so maybe what I should do is I'll rewrite f of x first is x times 4 minus x squared to the power of 1/2. And then I just want to highlight here, I need the chain rule. And here, I need the product rule. More practice with finding these derivatives. So now the derivative of this thing, the derivative of the first is the derivative of x, which is 1 times the derivative, or times the second, 4 minus x squared to the 1/2. Product rule I add, right? And so x times the derivative of 4 minus x squared to the 1/2 puts me at 1/2, the derivative of the outside evaluated at the inside times the derivative of the inside, negative 2x. Make sure you don't lose that negative. Bumped myself off the page here. Okay, so I can simplify this to be the root of 4 minus x squared plus, and I can do a little simplification here. 2 over 2 is going to go away, so that's great. And then I have to bump out that negative outside, so I get minus x squared, right? X times x is x squared, and that's over the root of 4 minus x squared. Let me just make sure. Yeah. So I need a common denominator here, and maybe I'll just move this over and multiply by 4 minus x squared over the root of 4 minus x squared, right? Forcing that common denominator so I can simplify. The root times the root is just 4 minus x squared, and then minus x squared all over the root of 4 minus x squared. I get 4 minus 2x squared over the root of 4 minus x squared. So now my critical numbers are either when this thing equals 0 or when the derivative does not exist. It doesn't exist when I'm dividing by 0, and it doesn't exist when I take the square root of a negative number, which on the interval, it's not going to be a problem, so we're going to ignore that. But I'll leave that there, and let you work on it, and I'll finish it in the notes, and then
at this point it's fairly straightforward. We're just figuring out where root 4 minus x squared is 0 or negative.
Totally. Yeah, so from this point, fly, you can do it. Just math now. Good. So give that a go. Also try the example that we skipped just to practice finding those critical numbers, and then check against the notes. Cool. Have a great Easter, and I'll see you on Wednesday. Weird.